Hi guys, welcome to ELEC142 Semester 2 Example Sheet 4 Solutions. This is part 1, and in this section we're going to look at thinking the first 4 questions, but we'll see how time goes. So this problem sheet is all about taking a series of resistors and inductors and capacitors and combining them to be one complex impedance. So to do this we need to take our components and we need to convert them into complex impedances. So this is the J omega L for inductors and minus J 1 over omega C for capacitors, and resistors stay the same. They're not frequency dependent and there is no imaginary part to them. So that's the key bit of information we have here is that omega is 500 radians per second, and this is our omega value for what we're going to calculate. So that's really important. So you're asked to modify the following circuits by replacing the components with a single complex impedance, assuming they're all supplied by an AC source operating with an angular frequency of that 500 radians per second. So the thing is, when you're working out complex impedances, is that they're dependent on frequency, and we're told for all of this problem sheet that it's this one constant frequency. This is our omega value. So let's start off and look at question 1. So what have we got? We've got a very simple circuit. It's a series circuit and we've got an inductor and a resistor in series. Our inductor has a value of 5 millihenries and our resistor has a value of 5 ohms. So let's go about solving that. So here are the written solutions, which you've got on Vital as well if you want to take a look. So what have I done? I've redrawn my circuit here. We've got our inductor and our resistor, and what I want to do is I want to convert it to become this single complex impedance, which I've called Z total. So the first step, I need to work out the reactances of each of these components. So that's XR and XL. And I've said before that the reactance of a resistor remains constant, there's no frequency component and there's no J component, so that converts to being 5 plus 0 J ohms to write it out in full. So that was the easy one. Then we're going to look at the inductor, X of L. We know that X of L is equal to J omega L, so we've got J times our omega value, which was 500, times the value of the inductor, which was 5 millihenries, and if you put those numbers in, that will give you 1 J ohms. But that's our J value, and because there's no real part, there's no component that doesn't have a J, we know that's 0, so we've written that out in rectangular form as 0 plus 1 J ohms. So what you'll see is I've written these both out in rectangular form. These are the full rectangular forms, and the reason I do that is it just makes it really easy to add them together. So to convert finally our Z total, because they're in series, we can just add them together. It's going to be XR plus XL, which is 5 plus 0J plus 0 plus 1J. Just add them directly together and it gives us a final answer of 5 plus 1J ohms. So that's the answer to question 1. See, that wasn't as bad as you thought it would be, was it? So question 2, again, it's very, very similar, but this time we've got a capacitor in series with a resistor. Our capacitor has a value of 60 nanofarads and our resistor has a value of 10 ohms. So let's do the same thing to solve that. Let's have a look. So question 2, what we can see here is we've got our series circuit again. We'll just unhighlight the first bit. We've got our series circuit, we've got our capacitor and our resistor, and what we want to do is convert it to this form where we've just got one complex impedance, which is Z total. That's what we're aiming for. So step 1, as before, we're going to find the reactances of each of these circuit elements. So first up, the resistor, that's 10 ohms, so that becomes just 10 ohms or 10 plus 0J ohms to present it in its full rectangular form. Then we can work out the reactance of the capacitor, X of C. We know that the reactance is minus J 1 over omega C, so what we're going to do is just put the values of omega and C in, which we've done there. If we work this out, this gives us minus J of 33333.3 J, but because there's no real part, we can put that 0 in the front, so that's the full rectangular form. And what I've done, just the next step, is I've rewritten it as 0 minus 33.3 K J ohms. Remember, resistances, we quite often represent them by Ks. That's absolutely fine to do. It doesn't really matter as long as it's clear to you what is going on. So that's all we've done there. So we found the complex impedance of each of these components. So now what we need to do is just add them together because they're in series. So that's what we've done here. So Z total is going to be the reactance of the resistor plus the reactance of the capacitor. Just taken these rectangular forms and put them here. So 10 plus 0J plus 0 minus 33.3 kJ is equal to 10 minus 33.3 J ohms. That's the full rectangular form. So that was question 2. So question 3. So that was a series combination of a resistor and inductor and a series combination of a resistor and a capacitor. So let's look at our next case. So our series case was our simplest one. So what happens when we move to components being in parallel? That's what we're looking at in question 3 and 4. So question 3 looks at the parallel combination of a 150 ohm resistor with a 30 millihenry inductor. So let's see what's going on. A lot of this is going to become very repetitive because the process for solving them is quite similar. So let's have a look at question 3. Don't worry by how complicated this looks. I'm going to break it down into smaller steps. Once you've got your head around what you're doing, the rest is just following through the maths and using our complex numbers and manipulating between polar and rectangular form to make the numbers in the most useful form for us. So what I've done is I've redrawn my circuit here with my resistor and my inductor, and what I'm aiming for going down is once again this one complex impedance component of Z total, and I've used a resistor symbol. That's fine. It doesn't matter that it's a resistor in parallel with an inductor because we're going to present the final value as a complex impedance which is in ohms, so it's absolutely fine to do that. So step 1 as before, we need to work out the reactances of each of our components. So X of R is the same as R, so that's just 150 plus 0 J ohms. The reactance of our inductor, X of L, is equal to J omega L. So once again, we're putting in the omega of 500, which we had at the beginning, and our L value of 30 millihenries, which we have here. So just put those numbers in, and you'll get 15J out of the end. And because there's no real part, we're going to write that in full form as 0 plus 15 J ohms. It's positive J here. Inductors are positive J, whereas capacitors are minus J. So for our total value, what we can see is that to find this, we need to look at the reactance of the resistor in parallel with the reactance of the inductor. So that's what I've done here. These two parallel lines are shorthand for parallel. You've probably seen this before. So that's good. The way we calculate this is we can use the same rules as we do for two resistors in parallel, is that it's the product over the sum. So we want the reactance of the resistor times the reactance of the inductor all over the reactance of the resistor plus the reactance of the inductor. So what I've done is I've just put the numbers into the equation here. So this one is the resistor, this is the inductor, this one's the resistor, and this one's the inductor. A note here, we've got multiplication at the top and addition on the bottom. Because we can convert between polar and rectangular really easily on our calculators, we're going to do that conversion to make the maths operation simpler. So if we're doing an addition, like we're doing on the bottom, we're going to keep it in rectangular form, and if we're doing a multiplication, we're going to put it into polar form. So that's what I've done. The next step is that I haven't done anything to these numbers. All I've done is converted into polar form. So what we have, the reactance of the resistor is a magnitude of 150 at an angle of 0 degrees multiplied by the value of the inductor, which is a magnitude of 15 at an angle of 90 degrees. Remember, when you've got a plus J, it changes to being an angle of 90 degrees when there's no real part. Minus J, as we'll see, becomes an angle of minus 90 when there's no real part. If you have a real part, you have to be a bit careful. You're better off doing it on your calculator rather than just looking at it and doing the straight conversion. You're less likely to make mistakes. So in the bottom part I said we leave in rectangular form, so we just add that together like we did in series. So the bottom part becomes 150 plus 15j. So far so good. Next step up here, I've done that multiplication. So I converted to polar form and then I did the multiplication. So what you do is you multiply the magnitudes together and add the angles. So I end up with a magnitude of 2250 at an angle of 90 degrees over this value. What this is simply the conversion to polar form from that rectangular form that we had in the step above. So it becomes 150.75 magnitude at an angle of 5.7 degrees. The reason I converted this to polar form is when we're doing division, polar form is the best one to work in. So that's what I've done there. So for polar division, we want to divide the magnitudes and subtract the bottom angle from the top angle. So that's what I've done here, and it gives me an answer of 14.93 at an angle of 84.3 degrees. That's the first bit, and that's the polar form. The final answer in rectangular form is, just to convert this number on your calculator, is 1.48 plus 14.86 j ohms. That's the final answer. So that's okay. For that question, it would be fine to give the answer in polar form without doing the conversion, because you weren't asked for a specific form to give the answer in. Note that normally these impedances are given in rectangular form because they're a bit easier to work out what's going on. And be careful in a question, if you're asked to give it in a particular form, make sure you do finish the question and do that. So let's do a similar thing for question 4. So this time we're looking at the parallel combination of a capacitor, which is 60 picofarads, and a resistor, which is 50 ohms. So we're going to follow the same procedure, it's just this time we've got a capacitor instead of an inductor. So let's see what that looks like. So question 4, I've redrawn my circuit. I haven't drawn a single combined impedance this time. I haven't shown what we're going for, but you've seen it so many times, you know it looks like we want to combine this to be one resistance, one complex impedance element. So find the reactance of our components. So for the resistor, that's 50 plus 0 j ohms. For the capacitor, it's minus j, 1 over omega c. So put the omega and c values in. Pico is an indice of times 10 to the minus 12. So that's what I've put in there, and it's minus j. So that gives us an answer of minus 3.3 times 10 to the 7 j. It's fine to express it in that form. Doesn't matter. It's easier to handle than writing out all those numbers. And to express that in its full rectangular form, we get a value of 0 minus 3.3 times 10 to the 7 j ohms. So that's step 1, work out the reactances. So our next step to find out what the total impedance is we want to look at the parallel combination of the resistor with the capacitor. That's fine. So I'm going to follow exactly the same procedure as we did for the one with the inductor. So we can use the same form as we did for the two resistors, where it's the impedance of the resistor times the impedance of the capacitor over the impedance of the resistor plus the impedance of the capacitor. So we've got this this product and sum rule again. So that's why we're going to follow the same procedure, because it's exactly the same thing with just some different numbers in. So the top one I convert to polar form because we want to do a multiplication. So that becomes 50 at an angle of 0 multiplied by 3.3 times 10 to the 7 at an angle of minus 90 degrees because it's a capacitor. So this minus j becomes minus 90 degrees because there's no real part, we can do that straight up. For the bottom, I've just added those components together because they're both in rectangular form already, so we get 50 minus 3.3 times 10 to the 7 j. Next step, what have we done? We've done the top part. The numerator is the phasor multiplication of those numbers, so multiply the magnitudes and add the angles, so we get 1.65 times 10 to the 9 or thereabouts at an angle of minus 90 degrees. And then the bottom part I've just converted from rectangular form to polar form. So that's what we've got there. You'll notice this has become pretty much, let me just highlight it to show you, it's become pretty much the same. We've pretty much ignored this 50. The reason we do that is this, you can do it on your calculator and you will get this conversion out, unless you've got a really, really, really accurate calculator that can show you lots and lots of decimal places. But what happens is, because this 50 is so small compared to the minus 3.3 times 10 to the 7j, what happens is that the imaginary component dominates the response. So that's why we end up with this precise value. But you should do the mathematics to make sure. You shouldn't just make that jump without actually doing the calculation. So let's do the phasor division. Now we've got it in this form. So we divide the magnitudes to give us approximately 50, and then we subtract the angles. So minus 90 minus 90 gives us 0 degrees. So our final answer is the total impedance is 50 plus 0j. That's the final answer. So you'll notice that what has kind of happened is that we've done this and we found out that it's pretty much equivalent to just having this resistor. And the reason for that is because at this frequency the capacitor is pretty much negligible. It contributes a very, very small amount to the complex impedance. But this is only for the value of omega. You'll notice as your operating frequency changes, your value of omega will change. So this is only true at this specific operating frequency. So that's it for part 1. Next up, we're going to look at the slightly more complicated versions. If you've got that so far, well done. Like I say, I think the main things you're going to find tricky are not the process, but actually manipulating the numbers. So make sure you're happy with converting from rectangular to polar form and back again, and how you do this polar multiplication and division. Those are the most common problems people have.